So in this video, I'm going to go through the reactions of alcohols to help you prepare for your upcoming test. I'm not going to go through any of 14.1, not because it's not important, just because I feel that you will be able to get the information you need directly from the booklet. So make sure that you can name alcohols, make sure you know the properties of alcohols and can compare the properties of alcohols to alkanes. Make sure you can draw these hydrogen bonding diagrams, very important to explain solubility and to explain their relatively high boiling points. Make sure you can classify alcohols, and then out of the reactions, I'm not going to go through the combustion of alcohols. Again, I feel that that's straightforward and you can get it from your booklet. Make sure you can write those equations and make sure you go through this experiment. It's actually from GCSE. It's how alcohols can be used as fuels. It's important. Make sure you go through it. I would advise doing all of this exercise here, exercise 1. I've provided you with the answers to those questions. The answer booklet is on Teams. So make sure you're going through these questions. They're similar to what you might see on the test, so there's definitely worth practicing. What I'm going to go through in this video is I'm going to go through the reactions, the oxidations of alcohols, the dehydrations of alcohols, and the substitution reactions of alcohols, just to supplement the information that's already in your booklet, just because it's a little bit harder and it might be harder for you to revise independently. But your test is pretty much split between the properties and the reactions, so don't just ignore everything else because I haven't gone through it in a video. So we're going to start with the oxidation of alcohols. You need to be able to classify an alcohol as primary, secondary, or tertiary. The alcohol I have just drawn is an example of a primary alcohol. It's primary because the carbon that is directly bonded to the OH, which would be this carbon here, is bonded to only one other carbon. Primary alcohols can be oxidized under 2 different conditions to form 2 different functional groups. If your primary alcohol is oxidized, and I use O in square brackets to represent oxidation, if it is oxidized using acidified potassium dichromate and distillation, you are going to form an aldehyde. If your same primary alcohol is oxidized using that same reagent, which is, acidified potassium dichromate, but you use reflux instead, then you're going to form a carboxylic acid. You need to learn this reagent off by heart, okay? It's potassium dichromate, and the H plus represents that there is an acid present. Instead of writing H plus, you could write H2SO4, or you could write the word acidified before your potassium dichromate. You can write the name of the reagent, potassium dichromate, or you can write the formula. You also sometimes see it as sodium dichromate, so you're just using a different alkali metal. And sometimes they can write it without the alkali metal at all, so it's just Cr2O7, and it has a -2 charge. This is all dealt with in the booklet, but just make sure that you can recognize that reagent every single time. There are a few different ways to represent it. As I said, if you oxidize a primary alcohol using distillation, you are going to form an aldehyde. So when I'm redrawing my product, I'm drawing it as an aldehyde. Common mistake in these oxidation reactions is that you change the number of carbons going from the reactant to the product. In my reactant, I've got 1, 2, 3 carbons, so I need to make sure that I'm only drawing 3 carbons in my product. In my reactant, I've got an OH on what I'm going to call carbon number 1, so I'm just going to number them as 1, 2, 3. I've got an OH on carbon number 1. It's an alcohol functional group on carbon number 1. Now in my product, instead of having an alcohol functional group on carbon number 1, I need to have an aldehyde functional group on carbon number 1. Aldehydes, double bond oxygen, single bond to a hydrogen. So that is what your product should look like. The other product that you make is water, H2O. What students always do is they do this, all right? They draw this structure and they do this when they're drawing it, and then they leave off the OH and they put in the double bond O. But in doing that, I've gone from having 1, 2, 3 carbons to 1, 2, 3, 4. It is so easy to add an extra carbon accidentally, okay? So just double check that you've drawn the right number of carbons, and I'm forming H2O. This is already balanced. I've got 2 oxygens on the left and I've got 2 oxygens on the right. If they asked you to represent this using structural formula instead of skeletal, structural, I've got a CH3 at the end, then I've got a CH2, then I've got a CH2 bonded to an OH. So that's my primary alcohol. I'm oxidizing it. I'm not going to write the reagent again, but it would be the same. And then when I'm writing my aldehyde, it's going to be CH3, CH2. And when I'm writing an aldehyde in structural formula, I write it as CHO. It has to be CHO, not COH. And then I have my H2O. Personally, I find skeletal formula easier. So unless they specify, I would stick with the one that you're most comfortable with. For me, that would always be skeletal. If they ask for structural though, this is the way you have to write it. Make sure you've got HO for the aldehyde. OH is not accepted. Underneath, I've got the same primary alcohol. I've got the exact same reagent, but instead of using distillation, I'm using reflux, and that changes the product. I'm still going to have 1, 2, 3 carbons, 1, 2, 3 in my product, but instead of having an alcohol functional group on carbon number 1, I'm going to have a carboxylic acid functional group. So I draw in my carboxylic acid functional group onto carbon number 1. Again, I need to make sure I've got the same number of carbons, and again, I'm forming H2O as an extra product. This time when I'm balancing, I'll see I've got 2 oxygens on the left, but I've got 1, 2, 3 on the right, so I need to put a 2 in front of that O. If I wanted to do this in structural formula, I would have CH3, CH2, CH2OH plus my oxidizing agent, and then when I'm writing the structural formula of my carboxylic acid, it's CH3, CH2, COOH plus H2O, and that is how it is represented. Okay, that's when I'm oxidizing a primary alcohol. Remember, this is primary because the OH that's bonded to the carbon is bonded to only one other carbon. You can also oxidize secondary alcohols. So this would be an example of a secondary alcohol. This is the carbon of interest. This is the carbon that's bonded to the OH, and it is bonded to 2 carbon atoms, not just 1. I'm going to oxidize my secondary alcohol using exactly the same reagent as I have above, potassium dichromate in the presence of an acid. And with secondary alcohols, we always use reflux, and with secondary alcohols, we always produce ketones. So again, I've got 1, 2, 3 carbons in my reactant. I want 3 carbons in my product. Carbon number 2 is bonded to an alcohol functional group. I'm now going to change it so that carbon number 2 has a ketone instead of an alcohol, and I'm also going to form H2O. Don't need to go back and balance this, it is already balanced. Structural formula would be CH3 at the end. Then here I've got a CH that is bonded to an OH, so I can put that OH in a bracket, and then at the end I've got a CH3. Okay, so I'm going from CH3 to CH with an OH, and then I've got CH3. You don't strictly need the bracket, although I typically tend to include it. Then I oxidize it using the same reagent, and then to show my ketone, it's CH3. Now instead of being CHOH, it's just going to be CO, and then at the end, I've got CH3. Again, you could put that O in a bracket if you wanted to, but typically a ketone is just represented like this. You've got a CO, then CH3, and then you've got H2O. You need to know the functional group changes. So primary with distillation goes to aldehyde. Primary with reflux goes to carboxylic acid. Secondary is always reflux, and it's a ketone. If you had a tertiary alcohol, which would look something like this, okay, this carbon is the carbon of interest, and it's bonded to 1, 2, 3 other carbons. It's a tertiary alcohol, and it cannot be oxidized, okay? So you don't oxidize a tertiary alcohol. So all you need to know is primary goes to aldehyde or carboxylic acid, secondary goes to ketone. When you're doing these then, it's therefore really important to see which type of alcohol you've got. And we've done a couple of these in class recently, and the one that tends to throw people off is, oh no, it's not that one. What one? There was one that I drew that threw me all off. This is clearly secondary. Hopefully we can all see that that's secondary. Oh, I know what it was. I drew it like this. I drew it like this. And because it was at the end of the chain, most of you looked at it and just immediately said it must be a primary alcohol. But let's look at the carbon that OH is bonded to. It is bonded to 2 other carbons. So just because it's at the end of a chain doesn't necessarily make it primary. This carbon is bonded to 2 carbons. It is a secondary alcohol. So when I oxidize this structure, okay, this is my carbon 1, 2, 3, 4. This carbon is now going to have a ketone there instead. So I've got a ketone there instead, okay, and I've also formed H2O. So make sure that you are checking what type of alcohol you have before you oxidize it. Make sure you're counting your carbons so you're not adding or losing a carbon along the way. Make sure that you know your reagent, and make sure you don't forget the water when you're asked to write an equation, okay? We just use O in square brackets to represent the oxidizing agent. You don't need to show the role of the potassium dichromate. So that is oxidation of alcohols. Let me find me another piece of paper. Let's do it on the back. That's oxidation of alcohols. Another reaction of alcohols that you have to do. Actually, hold on. Let me get fresh paper. Sorry, the other reaction we look at is substitution of alcohols. So here I'm starting off with my alcohol, and I'm going to substitute the OH, the alcohol functional group, for a halogen. It's just going to be a straight swap. So I'm going to redraw my carbons, 1, 2, 3, and then instead of adding an OH group to carbon number, I'm going to call that 1. Instead of adding an OH group to carbon number 1, I'm going to add a bromine to carbon number 1. So it's a straight swap, OH for a bromine. I lose the OH, it combines with the hydrogen, and I form H2O. Okay, I think the only reason this one can be a little bit confusing is that we don't actually use hydrogen bromide as our reagent. The reason hydrogen bromide is actually, it's quite dangerous and it's difficult to store. So rather than storing hydrogen bromide, what we do instead is we make hydrogen bromide in the reaction flask by adding in sodium bromide and an acid, H2SO4. And what will happen is the sodium bromide and the acid react in the flask to form hydrogen bromide, and then once formed, the hydrogen bromide will react with the alcohol. So what you do is you take your alcohol, you chuck in some sodium bromide, you chuck in some acid. The sodium bromide and the acid, they will react together to form hydrogen bromide, and then the hydrogen bromide that you have formed will go and react with the alcohol, and you will get this substitution reaction. So you need to be able to write this as an overall equation. So when the hydrogen bromide reacts with the alcohol, you're going to form what we had above, okay? But your other products that you're going to be left with are H2O, as we said, we had that above, but you're also going to have NaHSO4 as your third product, and that's typically the one that people forget. Okay, so 1 hydrogen and 1 bromine come together to form hydrogen bromide. So, you're taking the bromine and 1 hydrogen out to form hydrogen bromide. You're left with the sodium and 1 H and the SO4. And that NaHSO4 come together, and then your hydrogen bromide, as I said, reacts with the alcohol. The bromine takes the place of the OH, and you also form H2O. Okay, so, but these, I know that might even look a little bit complicated, but they're all exactly the same, so it doesn't matter what alcohol they've given you. There's an alcohol. I'm reacting this with sodium bromide and H2SO4. What I'm going to get is the bromine takes the place of the OH, so I put the bromine in place up there. I get my H2O and I get NaHSO4, so exactly the same as the one above. If I had a ring, students tend to hate rings. It doesn't make it any different. Okay, there's an alcohol. This time, actually, instead of using sodium bromide, I'm going to use sodium chloride, because instead of substituting bromine, I want to substitute in a different halogen, and I'm going to use the same acid. And again, all that's going to happen is the OH is going to swap places with the halogen. So I'm going to get Cl there. I'm going to form H2O, and I'm going to form NaHSO4. Make sure you can write that equation in full. If I take a different alcohol, Oh, this is the same. That's what I do a second ago. Let me try and make this more different. Oh, God, I don't know. I'll make it 2 alcohol groups. If I'm using 2 alcohol groups this time, and I'm going to use my NaCl, and I'm going to use my H2SO4, and I'm going to get 2 substitution reactions, which means I'm going to be forming 2 molecules of H2O, and then I'm going to have my NaHSO4. I would need to have a 2 there and a 2 there. So again, these reactions are always the same. You're just going to swap the OH for the halogen. Just make sure you are aware of your extra products. Make sure you are aware of your extra products so that you can write the full balanced equation. Last reaction is going to be the dehydration of alcohols, and it kind of does what it says. Right, there's an alcohol. Right, I've got my alcohol, 1, 2, 3, 4 carbons, and I've got my alcohol group, and I'm going to dehydrate this using concentrated acid. So I'm going to use an acid, and it's going to dehydrate. If I'm dehydrating something, I am removing H2O. I am going to remove H2O, but I'm going to be removing OH from 1 carbon, and then I'm going to remove a hydrogen from an adjacent carbon. So to remove H2O, I'm going to remove OH and a H. OH from 1 carbon, hydrogen from a carbon next to it. Now when I'm looking at this molecule, it's quite easy to see where my OH is going to come from. I've only got 1 OH. So this carbon here, carbon number 1, is going to lose an OH. Okay, so I'm removing OH from 1 carbon. It's going to be carbon number 1 that's losing OH. I now need to remove a hydrogen from the adjacent carbon. So adjacent just means bonded directly to. So carbon 1 is bonded directly to carbon 2, which means carbon 2 is going to be losing a hydrogen. Carbon 1 is going to be losing OH. So when I draw that out again, I'm still going to have 4 carbons. 1, 2, 3, there's 4 carbons. I no longer have an OH on carbon 1. I no longer have a hydrogen on carbon 2. That means carbon 1 and carbon 2 are both 1 bond short. So what I'm going to do is I'm going to put a double bond between carbon 1 and between carbon 2. And then my other product is the H2O that I've just removed. If we do another example, I'm just going to change it. I'm going to heat this alcohol with my concentrated H2SO4, and that's going to cause me to lose H2O. So again, I'm going to remove OH from 1 carbon, and that's quite obvious. I'm going to be losing OH from carbon number 2. But I need to lose hydrogen from an adjacent carbon. Now, carbon number 2 is bonded to 2 other carbons, carbon 1 and carbon 3. Carbon 3 has got 2 hydrogens. Carbon 1 has got 3 hydrogens. Both adjacent carbons have a hydrogen, so either of these carbons can lose that hydrogen, and you can form 2 different products. So I'm going to assume that it's carbon number 2 losing OH and carbon number 1 losing hydrogen. That's one possibility. So I draw my 4 carbons as always. I'm losing the OH, I'm losing the hydrogen from carbon 1. I'm going to form a double bond there. My other option is to again draw my 4 carbons. I'm still going to lose the OH from carbon 2. It's the only place I can lose OH. But instead of losing hydrogen from carbon 1, this time I'm going to lose a hydrogen from carbon 3. That means it's carbon 2 and carbon 3 that are each losing a bond. So my double bond is going to form between carbon 2 and carbon 3. And then I will have water as a product as well. So in some cases, when you're dehydrating an alcohol, you can form 2 products. I'm just going to do another one. I'm going to draw a ring, and I'm going to draw an OH. And I'm going to treat this with concentrated H2SO4. You do need to say the concentrated, and I'm losing H2O. So let's have a look. It's this carbon right here that is losing the OH. I'm going to call this carbon number 1. I'm going to call this 2, 3, 4, 5, 6. So the adjacent carbons are 2 and 6. They both have hydrogens. If I lose the OH from carbon number 1 and the hydrogen from carbon number 2, I will form this product. If I lose the OH from carbon number 1 and the hydrogen from carbon number 6, I will form this product. Now I know they look different the way I've just drawn them, but they're actually exactly the same. Because you've got a ring and all of the carbons are equivalent, I'm going to call this cyclohexene, I'm going to call this cyclohexene. There's no difference between these two structures. So you are only actually forming one product. Just one final one. Let me see, I want to do something. Okay, there we go. This is my alcohol. I'm going to dehydrate it, concentrated H2SO4. I'm going to be losing H2O. I'm clearly going to be losing my OH from this carbon here, which I'm going to call carbon number 2. And now I need to see where I'm going to lose my hydrogen from. So I've got 2 adjacent carbons. Carbon number 1 has got 3 hydrogens, so I could remove one of those. Carbon number 3, however, doesn't actually have any hydrogens to lose. Because it's got no hydrogens to lose, I'm only going to be forming one product, even though I do have 2 adjacent carbons. So I'm going to be drawing it out the same way as I drew it before. I'm losing the OH from carbon 2, I'm losing a hydrogen from carbon 1, and that is going to be my product. Sometimes I will see something that looks like this, where you remove the OH, you try and put a double bond between carbon 2 and carbon 3, but look at what you've drawn. Carbon 3 now has 1, 2, 3, 4, 5 bonds. That cannot happen. Okay, carbon 3 doesn't have a hydrogen to lose, so I can't draw a double bond between carbon 2 and 3. It has to be between carbon 2 and carbon 1. So that's dehydration of alcohols. There's lots of practice questions on this in your booklet. I've provided you with the answers for all of those questions, and you've also got some exam questions. You need to do lots of practice. Don't just read it. Practice answering the questions yourself, practice drawing out the molecules, and then mark your work. As you do the questions, you should be marking to make sure you're doing them right. You should be closely looking at the answers to make sure that what you've drawn is actually the same as what I have drawn. But if you've got any problems or questions with these reactions, just let me know.